Record. Okay. Now, hold on. Let me. Volume is not that high. Okay. So now let me go back to that question of why in some instances we are computing the entire naive Bayes equation, and in some instances we are not. Okay. So if we rewrite this equation here, we say that the naive Bayes can be probability of, okay, in this case here, I want to use the variables that we are using. CJ, okay, class, okay, CJ, the class, or just C, given D1, D2, D3, given those features, okay, is equal to probability of the features D1, D2, D3, given the class, multiplied by the probability of the class, divided by the features. So the question that we are trying to do is, sir, why is it that sometimes you consider everything, sometimes you don't? Okay, so one is the time that we can consider only certain things. Okay, when is the time that we are allowed to do all this? When is the time that we can only use the numerator, which in that example we already did, and when is the time that we can use only this part of the probability dependence? Okay, so in all of those cases, I want to emphasize that all of them are equivalent. Okay, equivalent to a certain sense. To a certain sense that there are assumptions that are being done, and then we say that they are not anymore that critical. Okay, certain things we don't consider because they are not critical. Okay, for example, you are saying that we want to take the probability. Let's just take, for example, the denominator first. Okay, so what is the time that we don't need to consider the denominator? Okay, so we're saying that in some cases we want to consider probability of, okay, CJ, yeah, or let's just say C1, C1. So now there's another C2, okay, given the same features, D1, D2, D3. Okay, then we can rewrite the whole thing. We can rewrite this probability of D1, D2, D3, given the class C2. Probability of C2. So divided by the same probability of the features. D1, D2, D3. Considering two classes of probability of C1 given the same features D1, D2, D3, Okay, we're given the same features, D1, D2, D3, and probability of those features, given those features, that this class, what is the probability of that class 1 given those features? And then what is the probability of class 2 given those features? Okay, now, because we're comparing two things, okay, we compare C1 class and C2 class, and both of them have the same denominator as probability of D1, D2, D3. It doesn't matter whether those numbers are included or not, right? It won't matter. It won't matter to the computation because they're the same factors. That means it is okay to disregard that. It is okay to disregard this because they're the same numbers that we divide to some numbers divided by the same factor, some number divided by the same factor when we are comparing the two things. Okay? You understand? So, for example, if this is 3, the numerator is 3 and the denominator is 2. The other one is 4 divided by the same thing, 2, because they have the same denominator. Yeah? Okay? This number, 3 divided by 2, 4 divided by 2, this one remains higher. Okay? Whether you cancel the 2 or you don't cancel the 2, you consider 3 only or 4 only, this one is still high. So we only consider the higher probability. So because we take the higher probability, say, oh, so this is the one that we prefer because that is more likely to happen because its probability is higher. Whether we say this is divided by 2, the result is 1.5. Divided by 2, the result is 2. This one is still high. So we say that this is still the higher probability. You understand? Nobody is saying anything. Okay? Okay, now that's one. Okay. That's the first instance of why, in some cases, we don't consider the denominator. Well, this is the complete equation. Okay, depending on this is a complete Bayes rule, depending on the number of features. Okay, we can write that in that example. Okay, but then because we are comparing two things, or we're comparing many instances, and the denominator are the same, so we can ignore them. So now the question is, sometimes you also ignore this part, the absolute probability for each class. Why? When is the time that we can choose to ignore them? We can choose to ignore them in some cases when we say the probability of each class is the same. There are equal probabilities of being class 1, class 2, or class 3. This, remember, in our cases of probably the balls, balls of the distribution, or the probability of considering which jar, okay, to choose, jar 1, jar 2, or jar 3. So in those cases, the probability are all the same. So 1/3 equal. So if they're equal, you can also disregard them because it doesn't matter on the final output. Okay, because we are comparing. Remember, we are comparing values. If you are multiplying certain number with the same, okay, with the same equal probability, the same probabilities, then the result won't matter. One number will remain higher with respect to the other. Okay, so that's the case. That in some instance, you might not consider the denominator because you're comparing two things. In some instance, you even disregard this absolute class probability because all classes have equal probabilities. Okay, and now when we say, okay, sir, okay, we can disregard them. Well, in this case, we are not disregarding. In this example, we are not disregarding. Why? We have to disregard, but in this case, we didn't disregard. Why do we still consider the entire equation in this case? You know what? Because we're only considering one class. We didn't consider it. We didn't consider sneezing against the other ailment. Hay fever against concussion like this. So if we have a flu, okay, of hay fever, okay, you have flu, hay fever, concussion, yeah. So flu, hay fever. Okay, now we only consider flu. What is the probability of it being a flu? Okay, so that's 66%. So we take that is already the total probability, very high, 66%. Now, if we didn't consider this bottom part, it's hard. We can choose not to consider the bottom part and compute for probability of the hay fever, given sneezing and builder. Okay, then the equation will be probability of sneezing and builder given hay fever and probability of hay fever. Okay, without going through the denominator. No, we don't need that. Then we take also probability of concussion given sneezing and builder is equal to probability of sneezing given builder, sneezing and builder given concussion, probability of concussion. Okay, so if we take this and we divide it with probability of sneezing and builder, and same thing here, we take the divided by probability of sneezing and builder. Okay, the same thing here, probability of sneezing and builder. Okay, if that is the case and we're comparing all the three probabilities, it doesn't make sense anymore to have this computation because we're already computing all three. So whether you include it or not, it doesn't matter. Okay, but because we only consider the flu only, so we don't compute this and we don't compute that, so we take the denominator because this is now the total probability of the flu given those symptoms. You understand? Okay. Okay. So what I'm saying here is that there are ways where you can simplify, and this is the way the method of naive Bayes. Where can you simplify? Okay, you can simplify. You can remove the denominator. Okay, that is not the full smile that we mentioned. It's just half the smile. Okay, despite the fact that maybe she really, really likes you, she doesn't want to say with the full smile because, if there's a way. Certain things are already done, so you don't need to do it. Certain things are, the denominator don't need to be computed because you are computing other ways. Okay, so in that case, you don't need, and so we can still come out with a certain conclusion that is valid. Okay, that's the idea. So now, the way this lecture is structured is not from the top to the bottom. It's from many. I don't also like it, but it's another way because some students can understand it that way. So another way of going through all the examples and then come out with a generalization. So somehow it's fine. Depending on which one is more effective for the student. Okay. So now, okay, this we have this example of estimating playing tennis or not. We have considered this many times, including in the. I think we have this in the Bayes rule. Yeah. So excuse me. So now we say given this table, and so you have the probabilities of different target values estimated by frequencies of 14 training examples. So in this case, you play tennis and you say yes. So how many are yeses? There are 9 divided by 14. And you play tennis, no. There are how many no's? That's 5 over 14. And so the probability of playing yes is 64%. Probability of playing no is 36% over 14 data sets. 14 training examples. Okay, so now we say that given this is just a way of again emphasizing on how you're going to take the probability. In this case, given that playing tennis is yes, okay, what is the probability that the wind is strong? Okay, so for the yes, you look at the wind that is strong. So this is yes. Wind strong, no. Yes. Wind strong, no. Yes. Wind strong, no. Yes. Wind strong. Wind strong, yes. So one. That's one. Yes, yes, yes. Two. Strong wind. Yes. Three. Strong wind. That's it. So there are three out of the how many yeses? 9 yeses. So 3/9 is 0.32. So it's just showing how you're going to count. Okay. So I think we have done this, but then we just emphasize playing tennis now and strong wind. Okay, no. And wind is strong, that's one. Okay, no, wind is strong, that's two. No, no, three. Three out of how many no's? 1, 2, 3, 4, 5. 3 out of 5. Okay, so okay, that's how you calculate. Okay, based on the table. So now there are two ways that we name those things that we use for doing naive Bayes. Okay, there are two methods. One is the maximum likelihood, the maximum priori method, and the maximum likelihood method. Okay, so again, those are simplifications of the Bayes rule. So now, okay, so in this case here, H map is the maximum a priori, is the case when you take the probability of a given H or probability of H given D. Okay, probability of a certain class H given the features D. Okay, is equal to, so this one. This one is, okay, maybe I should write it here so that it's clear. Okay. This is probability of H given D is equal to probability of D given H, probability of H divided by probability of D. You are familiar with this one, right? That is the Bayes rule. But now you have R max of H element of big H. Okay. Why is there R mark? What is that meaning? That H given a big H. Okay. So the meaning is you are taking maximum argument. Okay, the maximum of the result, the maximum argument. Okay. What this function, what this one, what is the result that gives us the maximum value? Okay, so in this case here, there are many cases of H's. So it can be H1. Okay, maybe it's better to have H1, H2, H3, like this one for H1, 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 and H1. Then you consider another H. Probability of H2 given D. Okay, and probability of H3. Now, you see what I'm heading to. Okay, so that means that we are going to consider all these computations of the classes given the same features, and we are going to compare which one is the maximum. Okay, because of that, the denominator you don't need. Okay, because of that, there's no need because it's the same value. So this one, the whole thing, this one is probability of D divided by H2, probability of H2 divided by, you get, yes, you get it right, divided by D. Okay? Now, the same thing here. Probability of D given H3 probability of H3, again, you guess it right, divided by probability of D. So in all these cases, we can disregard D. So D, disregard D, disregard D, and disregard D. So now, the maximum a priori equation is just the numerator. But you take the argument max. Argument max meaning you take the biggest number. Okay? This is the first estimation. Next, let's come to the last slide in this lecture. Okay? So now there's a much more, much simpler expression. Okay? So we go back at, we go back to the case of, how come my mouse is not doing well? Probability of your H given D is equal, probability of D given H, probability of H divided by D. So we're saying that in the first case, the a priori, maximum a priori case, the D's, we're consider all the cases where the D's are common denominator, and so we can disregard it. Okay? And in this case of maximum likelihood method, the maximum likelihood, we also disregard this to say that all the classes have equal probability. That is what I mentioned it already. So we can disregard this, that all the hypotheses have equal probable a priori. The same probability before, the same probability of occurrence. So probability of HI is equal to probability of HG. Probability of 1 is equal to probability of 2. Okay, so now, for example, we say that here you have probability of H1, just rewrite it, D is equal to, okay, probability of D given H1. I should change I thought this mouse is better. That's why I put it, but no, it's not better. That H1 divided by D probability, and then another one of probability of H2 given D. Okay, I know you understand it already, but I want to write it just to emphasize it. Probability of D given H2 and probability of H2 divided by probability of D. Okay, so the key word here that you need to emphasize is the argument max, this one. Argument max means that we are going to compare. We take the maximum argument. We take those with the highest computation. And based on the highest computation, you take the argument of what is that classification with the highest computation, then that is our choice. So now we just compare two. That means we want to compare which one is higher. So in this case, we know that we can disregard that because they are the same denominator. Now because we are saying in this case that you have uniform distribution, and then that uniform probability, that probability of H2 is equal to probability of H1. Because of that, these are all equal. This is equal and that's equal, so you can disregard that one as well, because they're just the same number. Okay, So you're left with just probability of now, that is the big D given H. Okay, so this is that one. So the probability of, it should be probability of the class H1 given D is equal to argument max of probability of the features D given H. Okay, and you compute all the possible possibilities of this. Any questions? Then you compare which one is bigger. No questions? That is our last slide. Okay, we're done with the naive Bayes rule. Easy? It's easy because it's just a Bayes rule. I just make it more, going around the bush so that, I give more examples and you enjoy and understand. But actually, I mean, it's easy. Okay, and it's just a matter of simplifying the equations based on certain assumptions. Okay. So I guess today you're ready. And if Camila, okay, let me turn off the recording now because we are just